Welcome, pre-calculus students. Today we're going to be continuing our examination of trigonometry. This particular part of trig is something you're probably used to seeing. I know you've covered it in geometry. At this point you've covered it probably in algebra too. We're going to be looking at trigonometry is with respect to specifically right triangles. We're going to kind of remove ourselves a little bit from the unit circle and some of the graphing. We're going to look at more specific examples. There's two special right triangles we've been looking at for a long time. In this point, there's the 30, 60, 90, 30 degrees. Oh, that's a 6. 30, 60, 90 degree triangle, and the 45, 45, 90. We've seen these before. Just to remind ourselves of the special proportions, which you probably help to figure out your values on a unit circle. Opposite of 30, we're going to call that side B. Opposite of the 60 is the square root of 3 times B. Opposite of the 90 is the 2b. You can verify these using Pythagorean's theorem. You can verify these in any number of ways. The opposite of the 45 is, if we call side A, opposite of the other 45 is A. Opposite of the 90 is the square root of 2 times A. For 30, 60, 90, the way I kind of remember this is that B is smaller than the square root of 3b, which is smaller than 2b, and the angles opposite of those are always the same. 30's got to be smallest. 30 degrees is smaller than 60, is smaller than 90, so they all kind of match up. But again, these shouldn't be any surprise. This shouldn't be any new information. These are things you should be used to seeing. So these are triangles we're going to keep coming back to, but they kind of help us figure out a couple special triangles later. When asking for the trig function of an angle, so when they're asking, hey, what's the sine of this angle, the cosine of this angle, the tangent of this angle, what we're really looking for is a ratio of certain sides. It's a ratio. It's comparing the different side lengths. And what's great is no matter how big or how small these triangles, if these two triangles are similar, the ratio of the sides are always the same. So that's why if we say something like the sine of 30, when we divide these things, the ratios, no matter how big or small, always come out the same. Here's the following sides. If we say here's theta, and this is 90. By the way, all of these times when we're looking at these are signs of acute angles. If we call this side, we'll say is A, this side is B, this side is C. Sine is the opposite side over the hypotenuse. Some of you may remember these for different ways. Sine, cosine, tangent. These are those are the old things like the old SOHCAHTOA, and if you've been in my class, you know I can't spell it, so I go with some old horse caught another horse, taking notes away. But these are ways. It's just the traditional definitions for sine, cosine, and tangent we've used before. In this case, opposite of theta is going to be the A, and the hypotenuse always remains the same as C. Cosine is the adjacent over the hypotenuse. The adjacent in this case to theta is B. Now, the hypotenuse is always the same. Hypotenuse is always opposite of the 90 degree. What's adjacent and what's opposite, though, those depend on what angle you're referencing from. So, example, the sine of alpha would be different from the sine of theta because opposite of alpha would be B, opposite of theta would be A. Tangent is opposite over adjacent. In that case, theta, opposite's A, adjacent's B. Now, cosecant, secant, and cotangent are the reciprocals of these other ones. So we can say that sine is, or cosecant's 1 over sine of theta. Secant would be 1 over the cosine of theta. And cotangent would be 1 over the tangent of theta. Another way of writing these would be treating these as multiplying the reciprocal. So that would be what would end up being the hypotenuse over the opposite side length. Secant would end up being the hypotenuse over the adjacent side. And cotangent would end up being adjacent over hypotenuse. If we were to associate those values, that would become B over A. Secant would become C over B. And cosecant would become C over A. These are, again, things you've probably seen before, things you're familiar with, so it's kind of just a review, but it's nice to see a little bit of an explanation. Maybe what you haven't seen before are questions like this. The tangent of alpha is going to equal to the square root of 3 over 5. What we have to do is find the remaining values of the trig functions. So in this case, we don't even need angles as long as we've got two of the sides. Anytime you've been given some piece of information, always helps just by starting to draw a triangle, specifically a right triangle. We're going to say this is alpha. Now, tangent is the opposite over the adjacent, which means the angle opposite of alpha is going to be the square root of 3. The side opposite of alpha is the square root of 3. The side adjacent to alpha is going to be 5. So, we've kind of labeled some of our information, but when we go to find the sine of alpha, we remember that that's opposite over hypotenuse. And we're kind of stuck because we're saying, wait a minute, I know the opposite. Opposite is the square root of 3. How can we find the hypotenuse? Well, go back to Pythagorean's theorem. 5 squared plus the square root of 3 squared equals c squared. 25 plus 3 equals c squared. C will equal the square root of 28. If you want to, you can abbreviate that, or excuse me, you can simplify that to 2 square roots of 7. So, we're going to take this, move it over here. We're going to take this, move it over here, and just go with c equals 2 square roots of 7. So opposite square root of 3 over 2 square roots of 7. The reason why we chose kind of some ugly numbers is we can get practice rationalizing. To rationalize the denominator, we're going to make this the square root of 7 over the square root of 7, which becomes the square root of 21 over 14. Cosine of alpha will equal the adjacent 5 over hypotenuse 2 square roots of 7. Rationalize the denominator to get 5 square roots of 7 over 14. We've got tangent, but we need the other three. The cosecant of theta of alpha is going to be, I'm going to go back to our original one just so I don't have to try to rationalize a couple times and simplify. So the reciprocal of square root of 3 over 2 square root of 7 is 2 square root of 7 over the square root of 3. When I rationalize that, that becomes 2 square roots of 21 over 3. The secant of alpha will equal, again, I'm going to go back to 5 over 2 square roots of 7. When I when I take the reciprocal of that, I get 2 square roots of 7 over 5. And I don't need to rationalize. I'm done there. And the only one we're missing is cotangent, which is going to be the reciprocal of tangent. Cotangent will equal 5 over the square root of 3. When I rationalize that, that becomes 5 square roots of 3 over 3.